At the very edge of our solar system, nearly 4 billion miles from the nearest source of warmth, there's a small, frozen world that should be completely dead. No atmosphere worth speaking of, no internal heat, no surprises, just a dark, icy rock drifting silently through the void. But the James Webb Space Telescope just detected something on Pluto that sounds physically impossible. It is actively producing complex carbon compounds using nothing but faint ultraviolet light and frozen gas. At the outermost fringe of our solar system, there's a world that is somehow generating more chemical complexity than everything the math said should exist there. And for years, the idea that Pluto could be doing anything chemically interesting made real planetary scientists roll their eyes. Then the James Webb Space Telescope turned its infrared eyes toward the darkness and proved something nobody was ready for. Pluto is not dead. It never was. This is the story of Pluto, the frozen world that science dismissed and then couldn't stop talking about. Stick with me, because by the end of this, you'll know exactly how a sunless, airless rock billions of miles away is quietly assembling the building blocks of life, and why that one strange fact might be a clue about how common those ingredients really are across the universe. Let's start from the beginning. Back in 1930, a 24-year-old farm kid from Kansas named Clyde Tombaugh was doing something nobody envied. He was sitting at a blink comparator at Lowell Observatory in Arizona, manually comparing hundreds of photographic plates, one agonizing pair at a time, looking for anything in the sky that moved. The process involved staring at thousands of starfields for hours, flipping back and forth between images taken days apart, hunting for a single dot that shifted position. Then, on February 18th, 1930, one dot moved, Pluto had been found. For the next 76 years, everyone grew up learning that Pluto was the ninth planet, the lonely sentinel at the edge of the solar system, a frozen mystery too far away to study properly. Then, in 2006, the International Astronomical Union reclassified it as a dwarf planet. The cultural reaction was almost personal. People were furious. Elementary school science projects were rendered obsolete overnight. Bumper stickers appeared. Pluto had fans. Here's the wild part, though. That demotion didn't make Pluto irrelevant. It actually set the stage for one of the strangest discoveries anyone has ever made about a world in our solar system. To understand why, you have to picture just how little we knew about Pluto for most of the 20th century. Even with our best telescopes, Pluto looked like nothing more than a blurry smudge of light. We couldn't map its surface. We couldn't measure its atmosphere with any confidence. We had no idea what it was actually made of beneath its faint spectral signature. Everything people thought they knew about Pluto was really just a guess built on top of another guess. Let's put its distance into perspective. If the sun were the size of a basketball, Earth would be about 26 feet away. Pluto, at its average distance, would be over a mile away, sitting in near total darkness. Sunlight reaching Pluto is roughly 2,000 times fainter than what we feel on a warm afternoon, and the surface temperature hovers around negative 380 degrees Fahrenheit. That is colder than liquid nitrogen. That is colder than most laboratory freezers on Earth can even achieve. So Pluto being frozen and dark isn't the surprise. Everyone expected that. The surprise is that it turned out to be doing something far more chemically active than predicted. Something out there was building complex molecules in conditions where chemistry was supposed to grind to a halt, and for a long time, nobody could explain what. Nobody even thought to seriously ask, because the assumption was so deeply embedded: Pluto is cold, Pluto is far, Pluto is irrelevant, that the question itself seemed almost pointless to pursue. Science sometimes works that way. The most interesting answers hide behind the questions nobody bothers to ask. The first real clue came in 2015 when NASA's New Horizons spacecraft finally got close enough to take a real look. What it found changed everything scientists thought they understood about Pluto, and it's exactly where our story needs to go next. But before we get there, I want to ask you for something small. If the kind of story you just heard, a frozen, dismissed world quietly breaking the rules of chemistry, is something you enjoy, hit subscribe right now. This channel is built around the strangest true stories in space science, the ones that sound made up until you look at the actual data. And I promise you, the part of this video about what James Webb found hiding in Pluto's atmosphere is even stranger than anything we've covered so far. You really don't want to miss that one. All right, let's keep going, because that first close look was only the beginning of the mystery. In July 2015, after traveling 9 years and more than 3 billion miles, the New Horizons spacecraft finally reached Pluto. It had exactly one chance to get this right. There was no slowing down, no second pass, no parking in orbit. It was moving at over 31,000 miles per hour, and it only had a matter of hours to gather everything it possibly could before Pluto shrank back into darkness behind it. What it sent back completely broke the picture scientists had built in their heads. Right across Pluto's face was a vast, heart-shaped plain of nitrogen ice nearly 1,000 miles wide, now officially named Tombaugh Regio, after the man who discovered the planet. It looked impossibly smooth, like a freshly poured floor, completely free of the craters that should have been scarring any ancient dead surface. Deeper into the landscape, towering mountain ranges of water ice rose nearly 11,000 feet, punching up from a nitrogen glacier like something out of a fantasy novel. At these temperatures, water ice doesn't behave like the ice in your freezer. It behaves more like rock, rigid enough to hold up mountain ranges for billions of years without flowing or collapsing. But the detail that really caught everyone off guard was the haze. Pluto had a layered photochemical haze rising more than 100 miles into its thin atmosphere, stacked in distinct bands like a tiny version of Saturn's atmospheric layers, glowing faintly blue in backlit images. Nobody expected a small, cold, seemingly inert world to have anything like a structured, photochemically active sky. At the time, scientists had no way to know exactly what that haze was made of. Was it just simple nitrogen particles clumping together in the cold, or was it somehow connected to something more chemically complex happening higher up in the atmosphere? New Horizons couldn't answer that. It got its one look, then raced on toward the outer darkness. Whatever secrets that haze was hiding, they were going to stay hidden until scientists found a completely different way to study them. What they needed wasn't another flyby. They needed something that could analyze the chemical fingerprints of Pluto's atmosphere in detail from far away without ever being anywhere near it. That tool did exist. It just hadn't been pointed at Pluto yet. And once it finally turned its attention toward that distant frozen world, everything scientists thought they understood was about to get turned upside down. The images from New Horizons had answered one set of questions, but in doing so, they had opened a door onto a much darker, more complicated hallway, and at the end of that hallway was something Webb alone could see. Here's what makes the next part of the story so different from everything before it. New Horizons worked like a camera on a speeding car. You get one drive-by, you grab whatever images you can, and then it's gone. But the James Webb Space Telescope doesn't work that way at all. Instead of flying past a target, it sits in a fixed point in space and stares, splitting incoming light into its component wavelengths, reading the chemical fingerprints embedded in that light like a barcode scanner, reading the molecular identity of whatever it's looking at. Think of it like this. Imagine you could tell exactly what someone had for dinner last night just by sniffing a sealed envelope they mailed you from across the country. That's kind of what Webb does, except instead of dinner smells, it's reading molecular signatures from nearly 4 billion miles away. There was a problem, though. Pluto is extraordinarily faint and extraordinarily far away. Its reflected light is buried under an enormous amount of noise, interference from background sources, and the technical challenge of resolving a signal from an object that, from Webb's perspective, is essentially a pinpoint. It would be like trying to read the label on a bottle of water sitting on the moon using a telescope from your backyard. Scientists had attempted infrared analysis of Pluto before using older instruments and kept running into walls, not because the chemical signatures weren't there, but because earlier instruments lacked the sensitivity to pull them cleanly out of the noise. Then in 2023, Webb's NIR spec and MIRI instruments were finally sharp and sensitive enough to change that. For the first time ever, scientists could pull detailed infrared spectra directly from Pluto's surface and atmosphere at a level of precision nobody had previously achieved, and what they found confirmed something researchers had been theorizing about for years, back when almost nobody believed them. Back in the early 2000s, a group of planetary chemists had proposed an idea that sounded almost backwards. Everyone knew Pluto was too cold and too far from the sun for any meaningful chemistry to happen on its surface. These researchers thought Pluto's atmosphere and surface might be doing something closer to the opposite. They believed it was synthesizing tholins, complex reddish-brown organic compounds built from simpler nitrogen and methane molecules broken apart by ultraviolet radiation, and then reassembled into something heavier and more chemically interesting. In other words, instead of acting like a passive frozen rock, Pluto's thin atmosphere would be acting like a slow chemical reactor, quietly building organic complexity out of the simplest possible ingredients. At the time, a lot of scientists thought this idea was reasonable in theory, but almost impossible to confirm without much better instruments. That changed when a team using Webb's data published results showing Pluto's spectral signature contained unmistakable evidence of ethane, acetylene, and a suite of heavier hydrocarbon compounds consistent with tholin production at concentrations and distributions that match the synthesis model almost exactly. Pluto's atmosphere really is building complex organic compounds, and the abundance turned out to be significantly higher than older models had predicted. Let that sink in for a second. Pluto isn't simply a frozen rock sitting passively in the dark. In a very real sense, it is actively assembling organic chemistry using nothing but trace ultraviolet light and molecules of nitrogen and methane. Scientists are now calling it an ongoing photochemical factory, one that doesn't match the behavior of any other known object at that distance from the sun anywhere in the solar system. The models that planetary scientists had relied on for decades, models that described the outer solar system as a place where chemistry slows down and eventually stops, where molecular complexity gives way to simple ices and inert rock, those models need to be revised, not tweaked, substantially reconsidered. Because if Pluto's chemistry is this active and this complex at 4 billion miles from the sun, on a fraction of a percent of the solar energy Earth receives, the outer solar system is not the chemically barren deep freeze science assumed it was. And here's the bigger question that discovery opened up. If a small, cold, sunlight-starved world like Pluto can quietly build complex organic chemistry using nothing but trace UV radiation and simple frozen gases, what else might the hundreds of similar objects in the Kuiper Belt be doing out there that we haven't noticed yet? That atmosphere turned out to be hiding one more secret, and it leads us straight into one of the strangest chemical relationships we've ever found in the outer solar system. Pluto has been slowly losing nitrogen and methane into space for billions of years. Gas from its thin atmosphere drifts upward, slips past the weak gravitational hold Pluto has on its outermost layers, and floats off into the surrounding void. Scientists already knew this atmospheric escape was happening. What they didn't know for a long time was where all that escaping material was actually going. It turns out it wasn't just disappearing, something was catching it. Charon, Pluto's enormous moon, orbits incredibly close to Pluto, just over 12,000 miles away, so close that the two of them are tidally locked together in a gravitational dance unlike almost anything else in the solar system. Both worlds always show the same face to each other, permanently. Most of Charon looks like a gray, crater-pocked surface of water, ice, and rock, except at its north pole. That polar region is stained a deep, rusty, reddish brown. For years, scientists suspected that dark cap was connected somehow to Pluto's escaping atmosphere. They just couldn't prove the mechanism in detail. Here's how the pieces finally fit together. Because of the way Charon is oriented as it orbits Pluto, its north pole spends roughly 100 Earth years in total darkness during Pluto's long winter. No sunlight reaches it at all during that stretch. That makes it an incredibly effective cold trap for escaped material. Escaping bits of Pluto's methane and nitrogen gas drift over, freeze directly onto that dark polar surface, and just sit there, piling up for decades, waiting. When Pluto's long winter finally ends and sunlight returns, something strange happens. The frozen methane doesn't simply evaporate back into space. Instead, ultraviolet radiation from the sun smashes the methane molecules apart and reassembles the leftover carbon and hydrogen fragments back together into heavier, more complex hydrocarbon compounds. Those new molecules don't evaporate. They stay locked on the surface permanently, deepening and darkening that reddish polar cap a little more with every single cycle, every single Plutonian year. In other words, two separate worlds, one slowly giving away pieces of its atmosphere, the other quietly catching them and converting them into complex organic chemistry, have been locked in this slow, steady chemical trade for longer than complex life has existed on Earth. And Charon had one more surprise waiting. Webb's detailed spectral analysis of the polar cap found signatures consistent with carbon dioxide compounds and possible water-ice interactions that nobody had confirmed there before. Just when scientists thought they had Charon fully figured out as a geologically dead moon with a quirky dark stain, it turned out to be far more chemically active and layered than anyone expected. The polar cap isn't just a stain, it is a record. It is a billion-year archive of everything Pluto has shed into space, compressed and chemically transformed onto the face of its closest companion. Think about that for a moment. Charon has been passively recording Pluto's atmospheric history in its polar chemistry for longer than complex multicellular life has existed on Earth. And we can now read some of that record for the first time because Webb gave us the eyes for it. So by this point, here's what we actually know. Pluto is building organic chemistry in its atmosphere. That same atmospheric material is slowly feeding Charon's surface chemistry. two worlds locked together, quietly trading pieces of themselves back and forth for billions of years, building complexity in the dark. But Pluto still had one more layer of mystery buried underneath all of that. And this next part might be the strangest piece of the whole story. Let's go back to Pluto's surface for a moment because New Horizons photographed something down there that nobody had seen anywhere else in the outer solar system. In a region scientists later named bladed terrain, enormous sharp ridges of methane ice rise hundreds of feet into the Plutonian sky, extending across hundreds of miles in parallel formations, all made of condensed methane ice sculpted by sublimation into blade-like vertical fins. Similar, much smaller versions of these structures actually exist here on Earth in high-altitude regions of the Andes Mountains in South America, where they form from snow sublimating in thin, dry air and rarely grow taller than an average person. On Pluto, that same basic sublimation process seems to have played out on a massive scale over hundreds of millions of years, carving those towering blades out of a landscape of pure frozen methane. Additional data from New Horizons suggests these features might cover as much as 15 to 20% of Pluto's mid-latitude region, spreading across the surface like the back of some enormous sleeping creature whose scales are made of ice. Not far from Tombaugh Regio, there are several enormous mounded structures that scientists still can't fully explain. Some reach miles in height and appear in irregular clusters with summit pits and collapsed flanks. They look structurally like volcanic calderas, except there's no silicate magma on Pluto. If these structures really are what they look like, they're cryovolcanoes, places that once pushed up not molten rock, but slurries of water, ammonia, and nitrogen from somewhere deep beneath Pluto's frozen outer shell. And that raises the single biggest question hanging over this entire story. If something underneath Pluto was warm enough and energetic enough to push material all the way up through miles of frozen nitrogen and water ice crust, what if that warmth is still down there right now? Scientists think it's genuinely possible that Pluto is hiding a liquid water ocean buried somewhere between 50 and 100 miles beneath its icy surface, kept from freezing solid by radioactive decay, still slowly radiating heat out of Pluto's rocky core. The idea sounds incredible, but the evidence keeps pointing that way. Tombaugh Regio's suspiciously smooth surface lines up exactly the way you'd expect if convection cells in a subsurface liquid layer were actively refreshing the nitrogen ice above it, the same way a lava lamp's blobs rise and sink, slowly churning the surface from below. And the cryovolcanic mounds sit directly above regions where something denser and less rigid than solid ice seems to be pressing upward from underneath, almost like dough bulging where yeast is most active. If that hidden ocean is really there, it has been sealed away for potentially 4 billion years, sitting in total darkness under pressures that would crush any submarine we've ever built, fed only by the faintest trickle of decaying radioactive heat. That would make it one of the most unlikely and most extraordinary possible places in the entire solar system where the basic chemistry of life might exist, cut off completely from sunlight, from warmth, from any external input at all. And there's one more piece to this puzzle that ties everything together, and it connects what's happening miles underground to what Webb found thousands of miles above the surface. Even the faint trace of ultraviolet radiation reaching Pluto is enough to break apart methane and nitrogen molecules high in its thin atmosphere. Those broken fragments don't just disappear into space. They slowly reassemble themselves into heavier hydrocarbon compounds, including tholins and nitriles, that drift downward and settle onto Pluto's surface, coating the terrain in that distinctive reddish-brown organic material visible in the New Horizons images. That same category of organic material, complex nitrogen-bearing carbon compounds, is part of a group of molecules some scientists believe may have once rained down onto early Earth during the heavy bombardment period roughly 4 billion years ago, possibly helping seed the oceans with the raw chemical precursors that life eventually emerged from. On Pluto, that exact same manufacturing process has been quietly running for roughly 4 billion years, a slow, steady chemical snowfall of organic building blocks falling forever onto a world simply too frozen and too isolated for any of it to ever spark into something alive on the surface. But what about 50 miles down, in the dark, where the ice meets liquid water that has never once been touched by sunlight? So here's where that leaves us. Pluto was never really the dead end everyone assumed it was back when astronomers first stripped it of its planetary status. It turned out to be the beginning of a whole new set of questions nobody had thought to ask. It sits inside the Kuiper Belt, a region of the outer solar system home to hundreds of thousands of similar icy worlds we've barely glanced at. If one small, dismissed, frozen dwarf planet was hiding all of this, a photochemical atmosphere actively building organic complexity, a chemical partnership with its own moon spanning billions of years, evidence of possible cryovolcanism, and maybe even a liquid ocean sealed beneath miles of ice. It is genuinely worth wondering what else might be sitting out there in the cold dark, patiently waiting for us to finally point the right instrument at it. James Webb is just getting started. Its observing program for outer solar system objects is still in its early years, and scientists are already lining up targets. Eris, Makemake, Sedna, Quaoar, and dozens of smaller Kuiper Belt objects whose surfaces and atmospheres we have never analyzed in detail. Every single one of them has been sitting out there running its own quiet chemistry for the entire history of our solar system. We spent decades assuming they were nothing worth looking at closely. Webb is already proving that assumption wrong, one infrared spectrum at a time. The Kuiper Belt, which we once thought of as a cosmic junkyard of leftover debris, is starting to look more like an enormous, cold, slow-motion chemistry lab. The question is no longer whether complex organic chemistry is happening out there. The question is how far it goes and what it might mean for the biggest question of all, whether the ingredients for life are truly rare or whether they are simply everywhere, quietly assembling themselves in the dark, waiting for the right conditions that may never come or may come more often than we ever dared to imagine. If this kind of story blew your mind a little, do me a favor, hit that like button, subscribe if you're new here, and turn on notifications so you catch the next one the second it drops. I've got more stories like this one coming, and you genuinely won't want to miss them. Before you go, I want to know what you think. If Pluto really does have a liquid ocean sealed away in total darkness 4 billion miles from the sun, running on nothing but radioactive decay heat for 4 billion years, what do you think could be down there? Or do you think it's just a cold pressurized layer of ice slush and nothing more? Drop your answer in the comments. I read every single one. And if you like this, go check out the video linked below about what scientists found hiding inside Enceladus's geysers. It might just be even stranger than this one. The universe does not reserve its most interesting chemistry for the warm, bright places. It runs in the cold, in the dark, in the margins. Pluto taught us that. We almost missed it because we decided it wasn't worth looking.